Hello everyone, this is our last example on mechanical vibrations, and we start with our standard equation that mx double prime plus cx prime plus kx equals 0, and we make the substitutions, so we have 2x double prime excuse me, plus 16x prime plus 40x is 0, and we'll just divide everything by 2, so we'll have x double prime plus 8x prime plus 20x is 0. And then we note that it is a second order homogeneous linear differential equation with constant coefficients. So we proceed with the characteristic equation, r squared plus 8r plus 20 equals 0. And this one, no matter how hard you try, it's not factorable. And so we're going to need the quadratic formula. So the roots are, by the quadratic formula, minus b, so minus 8, plus or minus square root, b squared, so 8 squared, minus 4 times a, which is 1, times c, which is 20, all divided by 2 times a, which is 1. So that gives us minus 8 plus or minus square root of, that's 64 minus 80 is negative 16. All over 2 times 1 is 2. So that's minus 8 plus or minus 4i divided by 2. And remember, we wanted of the form a plus or minus bi. The 2 goes in, divides neatly into 8, negative 8 that is, to give negative 4, and then plus or minus 2 into 4 2 times, so plus or minus 2i. Alright, so now we have complex conjugate roots of the form a plus or minus bi. So our general solution, we'll call it x of t, is equal to e to the ax, so e to the negative 4, e to the at, so e to the negative 4t, and then times c1 cosine of bt, so cosine 2t, plus c2 sine of bt, so sine of 2t as well. Alright, so then we are going to need the initial conditions, and to do so, note that x sub 0 equals 5 means that x of 0 is 5. And also, when we say v sub 0, it's really x prime sub 0. So x prime of 0 is equal to 4. And so we're going to need a derivative, but so we'll calculate that, x prime of t, and this is going to involve the product rule. So we'll have the first factor, e to the negative 4t, derivative of the second, derivative of cosine minus sine of 2t times 2, so minus 2 c1 sine of 2t, and then plus derivative of sine is cosine, 2t times 2, so plus 2c2 cosine 2t. Okay, so that's the first part of the product rule. First factor times the derivative of the second, now plus the second factor, what's in parentheses, times the derivative of the first, and the derivative of e to the negative 4t is e to the negative 4t times negative 4. So let's write negative 4 e to the negative 4t, and then times what's in parentheses here, c1 cosine 2t plus c2 sine of 2t. And I'm not going to bother cleaning that up because the initial conditions will unfold rather neatly, because we got sines and cosines involved, and as we know, sine of 0 is 0 and cosine of 0 is 1. So let's consider the first initial condition. Cx of 0 is 5, gives us 5 equaling, okay, going to x of t, e to the 0 is 1, cosine stays, sine goes away, because cosine of 0 is 1 and sine of 0 is 0, so it looks like immediately we get c1 is 5. And then the second initial condition, x prime of 0, which is really v sub 0, is given to be 4. So 4 is equal to, put that into x prime, all the e to the 0's are 1's. Sine of 0 is 0, so the c1 there goes away, and looks like we get 2c2. But then here, cosine of 0 is 1, sine of 0 is 0, so we get c1, but be careful. Make sure you recognize that the negative 4 is being multiplied by that c1. And so from that equation, we substitute our c1. So 4 is 2c2 minus 4 times c1 is 5. So then we get, let's see, that's negative 20, add it to both sides. 24 would be 2c2. So c2 is 12. Okay, so now our particular solution, x of t is e to the negative 4t, and then times the quantity c1 is 5, cosine 2t, plus c2 is 12, times the sine of 2t. Okay, so now we have to get it in our special form, and to do so, we start by focusing on what's in parentheses, and remember it takes the form of a cosine, say omega sub 0 t plus b sine of omega sub 0 t, but the point being that a is the coefficient that represents the horizontal axis, and b the vertical axis. So we've got 5 in the A direction, 12 in the B direction. That's going to be our triangle. Make a right triangle out of this. Maybe even label A as 5, B as 12, C, and also let's label our angle alpha. That is the actual angle alpha since we're in the first quadrant. And remember, we need 4 things: C, sine of alpha, cosine of alpha, and alpha itself. So to find C, we use the fact that C squared is A squared plus B squared. So then we have C squared is 5 squared plus 12 squared. So that's 25 plus 144. So then c squared is 169, and c would be square root of 169. Remember, the hypotenuse by definition is always positive, and the square root of 169 is 13. Okay, so now we need cosine of alpha. Cosine of alpha is just adjacent over hypotenuse. So these numbers are working out nicely. So a over c, or 5 over 13. Sine of alpha, opposite over hypotenuse, b over c, or 12 over 13. And then alpha itself. And since we're in quadrant 1, alpha is just going to be the inverse tangent of b over a. So that's the inverse tangent of 12/5. And if you're in degree mode, then that gives us 67.38 degrees. But remember, we have to report our answer in terms of radians. So multiply by the unit conversion factor, pi over 180, and we get 1.176 radians. Okay, so now we consider our particular solution, which was x of t, I'll rewrite it, was e to the negative 4t times the quantity 5 cosine of 2t plus 12 sine of 2t. And what we want to do is factor out the value of c. So we know that the value of c was 13. So if we factor 13, we have 13 e to the negative 4t, and then the quantity. Okay, this is easy to see, and even though it's an awkward factorization, but if I multiply 13 by 5/13, I get the 5, which is the coefficient of the cosine of 2t, and similarly, if we multiply the 13 by 12 over 13, we get 12, which is the coefficient of the sine of t. Now, the significance of that is the fact that, and it always works this way, the coefficient of the cosine and the coefficient of the sine, respectively, are always going to be the cosine alpha and the sine of alpha, respectively. So that we could replace the 5/13 by the cosine of alpha. So then in parentheses we have cosine alpha, cosine 2t, plus, and then the 12/13 we replace by the sine of alpha. So sine of alpha, sine of 2t. And then by our cosine of a difference identity, that is the cosine p cosine q plus sine p sine q, we have cosine of alpha minus 2t, because cosine p cosine q plus sine p sine q is the cosine of p minus q, so p being the alpha and q being the 2t, and then by the cosine of a negative angle identity, we saw we could switch the order. So the argument changes to 2t minus alpha, and then finally we could replace alpha. So we get 13e to the negative 4t times cosine of 2t minus the alpha. Again, you want to make sure you put in the radian value. Okay, so that's typical of the type you're going to get on the exam. I'm going to go over one more time without damping. With this particular problem, things get a little bit messy in terms of the coefficients, but still good practice to be able to see it. But the point being that on an exam, I'm going to design it, the problem, so that it works out nicely, like this one, where you end up with nice integer values rather than radicals, like we saw in the previous example, and I think we're going to see that again here. So to begin with, remember, they want us to use u of t. I'm not going to, I'll just make that note at the end. Replace x of t by u of t at the end. The given values were m equaling, I'll just recopy them here, 2c equals 16, k was 40, the initial conditions again were that x sub 0 was 5 and v sub 0 was 4. But when it's without damping, then we are taking the value of the dash pot c to be equal to 0. So now our standard formula, which was mx double prime plus cx prime plus kx equaling 0, becomes 2x double prime, c is 0, so the x prime's gone, and then plus 40 equals 0. Plus 40x, excuse me. Is equal to 0. Okay, so note that it can be divided by 2, maybe to make things easier, so x double prime plus 20x is 0, and then we consider our characteristic equation, noting that it is a homogeneous second-order linear differential equation with constant coefficients. So standard procedure, characteristic equation, r squared plus 20 would be 0. Okay, so there's a quadratic, but there's no linear term, so easiest thing to do, isolate the squared term. R squared is negative 20. That'd be r is the square root of negative 20, plus or minus, that is. So plus or minus the square root of 20 times the imaginary unit I. Okay, and I think what I'll do is I'll actually simplify that for this example. It is square root of 4, square root of 5 times I. So we get plus or minus 2 square root of 5 times I. But I'm going to say that 0 plus or minus 2 square root of 5i, because these are complex conjugate roots of the form a plus or minus bi. So therefore a general solution, again the textbook calls it u of t right away, I'm just going to call it x of t. If we want to call it u of t at the end, that's fine. But this would be e to the at, excuse me, so e to the 0t, and then c1 cosine of b is 2 square root of 5 times t plus c2 sine of the same 2 square root of 5 times t. And of course you're not going to leave either the 0 t in there, and in fact many of you won't even bother writing that step, and you'll just go right to the fact that x of t is c1 cosine of 2 square root of 5t plus c2 sine of 2 square root of 5t. Right, but to use the initial conditions, we're going to need a derivative, x prime of t, and that'll be minus 2 square root of 5 c1 sine of 2 square root of 5t, and then plus 2 square root of 5 c2 times cosine of 2 square root of 5t. Now we can go to the initial conditions. Okay, again, x sub 0 equaling 5 means x sub 0 is 5. So that means that 5 is equal to, we're going back to x of t, and substituting in a 0 for t, and cosine of 0 is 1, sine of 0 is 0, so right away we get c1. And then remember the initial condition that v sub 0 equals 5 really means x prime, because x prime, the derivative of the position is the velocity. So x prime sub 0 is 5, which further means, if you need to, x prime of 0 is, oops, it was 4, I'm sorry. So obviously we're going to fix that. Right, so v sub 0 is 4, which means x prime sub 0 is 4, and x prime of 0 is 4, which when substituted into x prime gives us that 4 is equal to, and then again the sine of 0 is 0, cosine of 0 is 1, so we get 2 square roots of 5 c2. Alright, so then c2 is going to be 4 over 2 square root of 5, or 2 over the square root of 5. And even though you might think to rationalize that, I think I'm going to leave that as it is. And so now our particular solution is, okay, so we're going back here to x of t, and that's c1, which is 5, times cosine of 2 square root of 5t, and then plus c2, which is 2 over the square root of 5, times the sine of 2 square root of 5 times t. Okay, so now we consider trying to obtain our special form of simple harmonic motion, which is c times the cosine of omega sub 0 t minus alpha. So we draw our sketch. We're again in the first quadrant, if you will, because remember, this always takes the form a cosine omega sub 0 t plus b sine of omega sub 0 t, where the vertical axis is the b-axis and the horizontal axis is the a-axis. They're both positive, a and b that is. So we're going to be in the first quadrant. You don't have to be to scale or anything. Just say maybe here and here. This would be the point, this would be our triangle, right triangle, of course, to the x-axis. Okay, alpha is going to be that angle. Could label the horizontal leg A, was given to be 5, and B, the vertical leg, 2 over the square root of 5. Alright, and then we need 4 things. The value of C, the sine of alpha, cosine of alpha, and alpha, the angle itself. So first the value of C, by the Pythagorean Theorem, C squared is A squared plus B squared. So that would be 5 squared plus 2 over the square root of 5 quantity squared. So that's 25 plus squaring the 2 we get 4. Squaring the square root of 5 we get 5. So therefore C squared is 25 is 125 fifths plus 4 fifths, 129 fifths. So then C is the square root of that. And I'm just going to leave it as the square root of 129 over the square root of 5. I'm not going to rationalize, because if we rationalize, excuse me, I think it's just going to make the computations more cumbersome. And so then we need the cosine of alpha. Remember, cosine's adjacent over hypotenuse, so A over C. So that's 5 over the square root of 129 over the square root of 5. So that would give us 5 square roots of 5 over the square root of 129. We also need the sine of alpha. That's opposite over hypotenuse. So 2 over the square root of 5 is B, the opposite, over C, which was square root of 129 over the square root of 5. And the square root of 5's cancel, and we get 2 over the square root of 129. Okay, and then we need alpha also. And fortunately, we're in quadrant 1. And in quadrant 1, alpha is just the inverse tangent of B over A. You have to be careful if you're in a different quadrant, and we'll see an example like that in class when we do our review for the next exam. And I think we saw an example earlier where we had to be a little bit careful because it was in a different quadrant. But when we're in quadrant 1, it's pretty straightforward because you just take the inverse tangent of B over A. B was 2 over the square root of 5. A was 5. So we get the inverse tangent of 2 over 5 square roots of 5. And if you're in degree mode, 10.1421 degrees. But we convert to radians, pi over 180. And that gives us 0.177 radians. And that's a 7 there. Just making it more clear. Okay, so now we go back to, or recopy it. X of t was 5 cosine 2 square root of 5 times t plus 2 over the square root of 5 times the sine of 2 square root of 5 times t. So we're going to factor out the value of c. That's our amplitude. which was the square root of 129 over the square root of 5. Okay, and then this will seem very awkward. In order to get this coefficient of 5, well, I can clear out this radical by multiplying it by its reciprocal, square root of 5 over square root of 129. So therefore it's just going to be 5 square root of 5 over the square root of 129. And then times the cosine of 2 square root of 5 times t. So that's easy enough to see, because the cancellations, of course. Now to get 2 over the square root of 5, well, I already have the square root of 5 in the denominator, but I have to cancel the square root of 129, and I've got the 2 in the numerator, so I'll leave that and just multiply by 2 over the square root of 129, because then the square root of 129s would cancel, excuse me, and I'd get 2 over the square root of 5, and then times sine of 2 square root of 5 times t. But remember, it always works out such that once we factor out the value of c, which again I'm just leaving as the square root of 129 over the square root of 5, that the respective coefficients of cosine and sine respectively are the values of cosine of alpha and sine of alpha respectively. So therefore we could replace the radical 5 over radical 129 by the cosine of alpha, and then we'll have that times the cosine square root cosine of 2 square root of 5 times t, and then plus 2 over radical 129 is the sine of alpha, so we'll have plus sine of alpha times the sine of 2 square root of 5 times t. But then we use our identity, give the coefficient, this is cosine p, cosine q, plus sine p sine q, which by our cosine of a difference between two angles is cosine of p minus q, so cosine of alpha minus 2 square root of 5 times t. And then our other identity is for the cosine of a negative angle, allows us to reverse this order. So cosine of 2 square root of 5t minus alpha. And now finally we replace alpha by what we had found. So we have radical 129 over radical 5, cosine of 2 square root of 5 times t minus, okay, again the radian version of alpha, 0.177. Okay, so that's actually the end of the material for exam 2. And there's some other things I'll show you about the graphs of these functions in class. And then we'll be doing a review in class to prepare for the exam.